Good morning, dear participants. Thank you for joining back. Our resource person will be joining very soon. So we will start our today's training program within a few minutes. Thank you. Good morning once again. Good morning, Ashwin sir. Thank you for joining again.
Good morning, Professor Feroz. Am I audible?
Yes, sir. Yes, sir. You're audible.
Okay, great.
Dear participants, now today's session it is starting now. You know that this is the second day of the training program. So, like the previous day, we will be having three sessions today. So, today's first session, it will be starting with a talk by Professor Ashwin Ganesan. So, let me give a brief introduction about Professor Ashwin. Professor Ashwin is an associate professor at the International School of Engineering, that is INSOFE, Mumbai, Maharashtra, India. His research areas include distributed algorithms, graph and algorithms in communication networks, discrete mathematics and graph theory, interconnection networks, applied combinatorics, and graph algorithms in data science. His research results have been published in various journals, such as IEEE Transactions on Communications, Linear Algebra and its Applications, IEEE Transactions on Information Theory, and many more. I formally once again I welcome Professor Ashwin to this training program. Thank you, sir, for joining this training program. Now it is over to you. Thank you, sir.
Thank you very much, Professor Feroz, for the kind invitation to give a lecture at this workshop. I just have a quick question before I get started. When I unmute, when I sort of turn on my camera, it gets turned off automatically. Is there a way to have my camera turned on?
I guess from here there is no option for making your camera on. So probably you can do one thing. You can leave the meeting and join once again, so that
Okay. Okay, I'll try that. Okay.
Yeah. Dear participants, a resource person will be joining back within few minutes.
Okay, I think the same issue is still there. That's okay. I think I'll go ahead and present without the video. I mean, the audio I think is okay. It's enough.
Yes,
Let me
yes, sir.
share
Yes,
my
sir. Please do
screen
that.
here. So is my are my slides visible?
Yes, sir. It is visible. Introduction to hash tables.
Yeah. Okay. Great. Okay. So I'm going to be talking about hash tables, which are, very ubiquitous data structures. So they arise in many different problems in big data. If you want to have good performance, hash tables are basically very widely used to achieve that performance. What I'm going to do today is basically introduce the notion of hash tables. I mean, in many faculty development programs, the material that's covered is sort of a little bit more advanced than what you cover in your classes or when you teach. So this is going to be the same here. I'll probably give you a somewhat rigorous introduction to hash tables. Um, so the goal here is that basically you can imagine that you have some real world problem where you have some data to store in some kind of a dynamic set, and you want to be able to insert new elements into that set. You want to be able to search for elements in that set, and you want to be able to delete elements from that set. Now, you could use data structures like arrays, linked lists, and so on. All of them have a worst case running time, which is linear for at least one of these operations. What we want to do is be able to do better than that. And it turns out that if you use hash tables, then we can achieve constant time performance on the average for all these three operations. The worst case performance will still be linear time, but basically in practice and in most situations, you end up achieving a constant time. So one of the simplest kinds of hash tables is called direct address hash tables. Basically when so what you want to do in these in this real world problem is store a bunch of key value pairs. For example, the key could be, for example, these key value pairs could correspond to words K and their meanings V in a dictionary. So in a real English dictionary, you have words and their meanings. And when you search in the dictionary, you search using the key K, using the word, but really what you're interested in is the meaning of the word. And so that's the satellite data that you end up retrieving. Another example would be, before we had online phone directories like we do today, many cities had their phone directories in a book. You had this huge, 1,000+ page book with people's names, an address along with a phone number. So what would uniquely identify the key of a person, the identity of a person would be the person's name and their address. And then if you knew exactly whose phone number you were looking for, you could go ahead and find their phone number. Or you could think of it as maybe K is a student ID number at a particular university, and maybe V is their transcript. So basically, you want to store a collection of key value pairs. The simplest way to store them is actually called direct addressing. And what you do is you store the key value pair K in slot number K of an array. So you create this huge array. And every possible key in the universe corresponds to a unique slot in the array. For example, if the key is the student ID number, then, by the way, I think I hear some slight background noise from the other side. Maybe that's not from me. Maybe that's my own echo. Let me see here. Yeah, go ahead. Am I audible, by the way? Is my voice clear?
Yes, sir. Your voice is clear,
Yes, sir.
sir. Yes, sir.
Okay, great. So, you can imagine if, let's say that, the universe of all possible keys is just 0 to 9. Let's say you want to only store so what you do is, because the universe is 0 to 9, you create an array with these indices 0 to 9. Basically, you create an array of length 10. And if you only want to store 2, 3, 5, and 8, you store them in positions 2, 3, 5, and 8 respectively, like so. So, for example, you could initialize your array to be an array of 10 pointers. And then whenever you want to insert an element, you change the null pointer to point to a new cell that's created dynamically during runtime. For example, in C, there's the malloc command to do a memory allocation at runtime, and you store the data right there. The problem is, if each of these keys was, for example, an 8-digit student ID number, let's say student ID numbers were 8-digit numbers, then the universe of all possible keys would have, 10 to the power 8, which is 100 million different elements. And so you would have to initialize and create an array of 100 million slots, even though you might only actually end up storing data in about 2,000 of those slots. You only might have 2,000 students. So one disadvantage with this approach is that sometimes the universe U of all possible keys is much, much larger than the actual number of keys that you end up storing. Sometimes the universe U might be so large that you might just not even have enough space in your computer to create this array. On the positive side, the advantage of using such a data structure is that you can do all of these three operations. These three operations are part of the dictionary abstract data type. You can do all of these three operations: search, insert, and delete, in constant time in the worst case. So if you want to know if you want to search for element 6 and you want to know if element 6 is present, you just index into the 6th slot of the array and see if there's any element there. And indexing, given the index, accessing that particular location in the array can be done in constant time in modern computers. So search, insert, and delete can all be done in constant time in the worst case. But like I said, this is not feasible if the universe U is very large. By the way, a lot of those images that I'll show in the slides are taken from that popular CLRS textbook by Corman, Leiserson, Rivest, and Stein. So in case you want to sort of, I'm going to do some mathematical analysis and probabilistic analysis of hash tables and when I analyze their performance. So if you want to sort of read through it more slowly, you can always read it from that particular textbook. So when you cannot really allocate 1 unit of memory for each key in the universe, we need to somehow come up with a more memory efficient way to store this data. You want to be able to store element I in the ith slot, because then you can determine whether I is present in the array, you can access the satellite data and so on in constant time. And we can basically do something like that, pretty much like that, without consuming a whole lot of memory. And the hash tables let you do that, but the only problem is that we'll be able to get the big O of 1 performance as only as an average case performance, not as a worst case performance. So it turns out that in practice and on the average and in most situations, hash tables take big O of 1 time per operation, even though for some of the operations it could take linear time. When you do an amortized analysis, you find out they actually perform in constant time on the average. So so if you want to store a set of key value pairs, what you do is you create an array of pointers. You initialize your data structure to be an array of pointers, and given any key k and its satellite data, the slot in this array where you would store the key and its satellite data is slot number h of k, where h is called the hash function. So the hash function h maps the universe U of all possible keys into one of m possible slots. And that way, even if the universe U of all possible keys is extremely large, for example, even if the universe U contains all the 10 to the 8 8-digit numbers, if you only want to store 2,000 elements, you can create an array containing 2,000 slots. So M would be 2,000, and any of those 8-digit numbers would be mapped to one of these 2,000 slots. And so the range of array indices in your storage can be much smaller than the universe U. Much smaller, yeah. The number of different, well, the size of the array that you need to allocate in the beginning can be much smaller than the size of the universe U. So basically, here we're seeing an example where the universe U could be very large. Let's say it contains 100 trillion keys. Maybe you only want to store, a few keys. What you do is you create about m slots. If you want to store 10 keys, normally you would create an array of 10 slots. And then if you want to store K1, you would store it in slot number H of K1. Of course, what can happen is you can have two different keys being mapped to the same slot. You can have two different keys hash to the same slot. And when that happens, we say that collision has occurred. Now, definitely, if the number of different keys that you want to insert is more than the number of slots, then by the pigeonhole principle, you will surely have at least one collision. What is interesting is that even if the number of different keys that you insert is less than or equal to the number of slots that you've allotted, it's still possible that a collision can happen. And in fact, even if the hash function, is a good hash function, and it uniformly distributes the keys to the different slots, there's actually a pretty high probability that you'll have a collision. And I want to kind of illustrate that with a toy problem called the birthday problem. Okay, so this is, this doesn't, so understanding this particular slide does not require anything to do with hash tables. Doesn't require anything about, what we've covered so far in hash tables. It's kind of an independent standalone slide, and it's a very interesting problem that you come across when you study probability theory, and it's called the birthday problem. Suppose that there are n people at a get-together. The question is, what is the probability that some two people have the same birthday? So let's say, for example, that the number of people is 23. So let's say you go to a get-together. Okay, you and your friends are to get together, and at that get-together, maybe it's a department social gathering, and let's say that at that department gathering there are 23 people. What is the probability that some two people among those 23 people have the same birthday? Meaning, what is the probability that some two people were born in the same day of the year? Now, you might think, well, there are 365 days in a year. Let's assume there are 365 days in a year. So let's ignore leap years, okay? Let's just say, for the sake of this problem, that there's only 365 days in every year. You might think that, if there's 23 people but there's 365 different days in a year, then the probability that every person is uniquely assigned a random day of the year. So let's say that you have these bins, Jan 1st, Jan 2nd, and so on, all the way up to December 31st. So you have these 365 bins. The first person is randomly put in one bin. Another person is randomly, so for each person, one of the 365 bins is selected uniformly at random, and the person is put into that bin. So if you put 23 people into 365 bins, what is the probability that some bin contains 2 or more people? That's really what this question is asking. Now, you might think 23 is much smaller than 365, so the probability is pretty small. But you can go ahead and do an analysis, and it's pretty surprising. The probability is actually more than 50%. So the probability that some 2 people share a common birthday is 1 minus the probability that all 23 people have different birthdays. Now, if you take these, let's say you have 23 different people. For each person, you're going to be assigning a unique birthday. How many different ways can you do that? For the first person, you can choose any of the 365 days as a birthday. So there's 365 ways to assign a birthday to the first person. For the second person, so the question is, in how many different ways can you assign birthdays to these 23 people so that everyone has a different birthday? So for the second person, there's 364 different ways to choose a birthday, because you can choose any birthday for the second person which was not already assigned to the first person. And finally, for the last person, there's 343 different ways to choose a birthday. And so the total number of different ways to assign the total number of different ways to put these 23 people in these 365 bins is 365 times 364 times 363, and so on, all the way up to 343. But that's the numerator. We're looking at the probability that all 23 people have different birthdays. So that's basically a ratio. The event. So when you randomly allot birthdays to people, the event that all 23 people have different birthdays has this many different outcomes. That's the numerator. The denominator is the size of the sample space, which is all the different ways in which birthdays can be allotted. So that ratio is that probability we're looking for, and that's exactly here. You can even obtain this ratio another way by using the notion of conditional probability. The first person can be given a birthday with probability 1. The probability that the second person has a birthday different from the first person is 364 or 365, and so on. So using the notion of conditional probabilities, you can get the same answer. But anyway, it turns out that if you have 22 people, that this probability is about 49%. But once you have 23 or more people, this probably exceeds 50%. And if you have like 30 people, I think this probably is pretty high, maybe more than 75%. If you have a 50 people, it's very surely more than 99%. That's kind of very counterintuitive, and that's why sometimes this problem is called the birthday paradox. It's a paradox because it's very counterintuitive, but it's actually, you can prove it mathematically rigorously that these probabilities are much higher than what you would expect. Okay, so if you were at a party with your friends, and if your friend doesn't know probability theory, then just for fun, you can make a bet with your friend. Let's say there's 30 people at the party. You can make a bet and say, hey, how about let's have a bet? I bet some 2 people have the same birthday. Maybe you can have a bet for 10 rupees just for fun. And if your friend doesn't know about this problem, he or she will agree to the bet, and you can basically win the bet. But basically, the relevance to hash tables is the following. Even if you create 1 million slots, okay, the slots in a hash table are sometimes also called buckets. Okay, so even if you have 1 million buckets in the hash table, and you're only placing about 2450 keys, about 2450 keys into these million buckets. And even if you have a really, really good hash function, which does a really good job of basically allotting the keys randomly to the different buckets, the probability that some two keys will be colliding and basically hashed to the same slot is basically about 95%. What I'm saying is that when you create a hash table like so, to store the data, you have to have some way to address collisions, because collisions can occur with a very high probability, as we're seeing here from these calculations. Any questions so far? Maybe I'll just take a minute here to pause. Okay, so far so good then. Let me continue to the next slide. So one way to resolve collisions is by doing something called chaining. What that means is that when you have two different elements which hash to the same slot, you put all of them into that same slot. Obviously, if you have just an array, each cell in the array can only store one element. So what you do is, instead of creating an array of, let's say, integers, you create an array of pointers. Initially, all of those pointers are initialized to be nil. And then whenever a key which needs to be inserted hashes to a particular slot, you go ahead and insert that key into that slot by creating a linked list emanating from that particular pointer. So instead of the pointer being nil, you would go ahead and during runtime, you would use the malloc command to, some kind of a memory allocation command, which would create a new cell at runtime. You would store the data there, and you can insert a new element at the beginning of a linked list in constant time. And so you can go ahead and do that. So the way to handle collisions is basically by doing what's called chaining. Let's go ahead and work out an actual example of how chaining works. So in this exercise, we're going to see what happens when we insert these keys, 15 to 75, into a hash table with collisions resolved by chaining. So what you would have is a hash table which is initialized to be an array of 10 pointers. I hope you're able to see my writing here. And we will create an array of 10 pointers and initialize the array to be all nil pointers. So I have sort of depicted the fact that a cell, a particular pointer is nil by putting a dot there. In many, another way to do it is by putting a slash. But in any case, what happens when you want to insert 15 into this particular data structure? So this is our initial data structure that we're starting with, and we're going to be now modifying the data. So 15 goes, you compute h of 15, which is 15 mod 10, which is 5. So you're going to be inserting 15 into slot number 5. Now, I know many of you might have seen hash tables before, but we'll do a more, a mathematically rigorous analysis of its performance pretty soon. I just want to make sure everyone's on the same page before I do that, so I'm doing a simple example here. So 15 goes there. 7 mod 10 is 7, so 7 goes into slot number 7. 33 goes there. 46 goes there. 96 goes there. Now, you could decide to insert new elements at the beginning or at the end. I've decided to insert new elements at the end of the linked list. Either of those operations actually can be done in constant time. It's actually pretty easy to insert at the beginning of a linked list in constant time. But if you always maintained the address of the last element on a linked list in a special variable called a rare pointer or something, then you can go ahead and insert at the end as well in constant time. So 21 goes there, 34 goes there, 10 goes there, and 75 goes there. So so if you want to store this data, you could store it in an array where all the elements are stored, one after another, like so. That's one data structure. Another data structure would be a linked list containing all the elements. But another data structure, another way to store the same data is a hash table. And you can see here that there's trade-offs involved. This particular hash table, maybe takes up slightly more storage space than a linked list. But you can see that if you want to search, for example, if you want to search for the element 63 in your set and return whether or not the element is present, you can do it very efficiently here in the hash table, because you compute the hash value of 63 mod 10, which is 3. You know that if at all the element 63 is present, it's present in that particular linked list, and so you can quickly check through it. So if you have, for example, 10 elements inserted into a hash table that has 10 slots, then you have 10 linked lists that you've created, but some of them could be empty, and the average length of a linked list is 1. Right? If you have 10 elements in 10 linked lists, then on the average, a linked list has 1 element. And so searching through a linked list that has only 1 element can be done very quickly. And the hash function is always assumed also to be computable very efficiently, basically in constant time. And so the search operation, which involves first doing a constant amount of work to compute the slot number, and then inserting that, which requires another constant amount of time, can both be done very quickly. So that's all basic stuff. I assume many of you have seen everything I've told you so far. In Python, you can, so the point here is that on the average, every linked list has linked 1, and so you can do insertion, search, and delete all in constant time on the average. Of course, the worst case running time is still linear, because in the worst case, all the elements would hash to the same slot. And so you would have this kind of a performance of a linked list. So if you're unlucky or you're not using a good hash function, then all the elements will hash to the same slot, and you'll have a single long linked list. So hash tables have the same worst case performance as linked lists, but they have better average case performance. In Python, for example, if you wanted to create a hash table, one way to do it is to create a list of lists. So if you had 10 slots, you would initialize your hash table, which is a list of 10 lists, to contain a list of 10 empty lists. And then if you wanted to insert, for example, the element 15, you would find the slot number is 5 and then insert it into the 5th list. So anytime you wanted to insert an element, you would insert it into the appropriate list. And so you would end up getting this particular thing here. Okay, and why would you want to store the elements as a list of lists like this rather than as a single list? Well, we saw why. If you want to search for the element 63, for example, you only have to search this particular sublist rather than the entire single list, right? So now comes the more difficult part. What is the performance of the hash table? So if you end up doing hashing with chaining, on the average, how long does it take to search for an element with, in that particular data structure? And one of the parameters which arises, well, basically the ratio of n over m arises often in our analysis. So n is the number of elements in the hash table, and m is the number of slots in the hash table. So if you've inserted n elements into m slots, then the average length of a linked list is n over m, which I'm defining to be alpha. And alpha is called the load factor. So the load factor basically is the average length of a linked list. And it can be, anywhere from less than 1 to 1 to greater than 1. Now, in the worst case, all the different keys hash to the same slot, and therefore the worst case performance of any of these three dictionary operations, insert, search, and delete, is going to happen for example, for the search function. For the search function, if you want to search for an element in a linked list, in the worst case, you search through the entire linked list, and then you return a negative answer that the element is not in the linked list. So basically, the worst case performance of search is linear time. The time to compute a hash function is big O of 1. So big O of 1 plus big theta of n is just big theta of n. Now, what about the average case performance? Well, we're going to have to make some assumptions now on the hash function and on the data. And you could have an adversary who picks the data to be such that all of the elements always hash to the same slot. And so we'll have to basically make some probabilistic assumptions on the data in order to do this analysis. And one assumption which is commonly used is called simple uniform hashing. And under this assumption, basically, you have, first of all, a uniformity assumption that whenever you're given a key, it's equally likely to be placed in any of the m slots. You have that's kind of some uniformity assumption, and that probability. So the probability that a key goes to slot number I is 1 over m for any slot. Okay, so and that's regardless of where any other element has been hashed to. So basically, mathematically, what we're saying is that if you're given any two distinct keys, ki and kj, in the universe U, then we're going to assume here that the probability that h of ki equals h of kj is 1 over m. One way to think of this is that h of ki, regardless of where a key ki goes to, the probability that key kj goes to that particular slot is just 1 over m. So it's sort of like saying the probability that some two people, ki and kj, have the same birthday is 1 over 365. So my birthday is April 29th, and the probability that somebody else has the same birthday as me is 1 over 365, and that can be shown, right? And let xij be the indicator random variable. So it's basically the indicator random variable of the event that h of ki equals h of kj. And an indicator random variable takes values 0 or 1. So the expected value of an indicator random variable is just the probability that that indicator random variable takes the value 1 and hence is equal to 1 over m. For each of the m slots, the average length of a linked list in that slot is alpha, right? Because if you place n elements in m linked lists, then the average length of a linked list is alpha. So if you're searching for an element in a hash table, then the average, so once you create the hash, once you compute the hash value, you know the slot number where you need to search for that element, and the complexity of the search operation from that point onwards is linear in the size of the linked list. And the size of the linked list is alpha on the average, and therefore the total cost of searching for an element unsuccessfully in a linked list is 1 plus alpha. So basically, I remember in an unsuccessful search, you would compare the element you're searching for with each of the elements in the linked list, and then return a negative response that the element is not present in your linked list. But that's the worst case thing that can happen. It's an unsuccessful search. And in that case, the number of elements in the linked list is alpha on the average, and computing the hash function has a cost of 1. And so the total cost of the entire search operation is big theta of 1 plus alpha. Now, what happens if you do end up finding the element in the hash table? So you have this hash table, and in a particular slot, you have basically several elements, and maybe you have xi there, the ith element. Let's say the elements which you're inserting, so you insert the elements x1, x2, up to xn, and there's your xi, okay? If the search is successful, then what is the complexity of that search operation? Basically, what you would do is you compare the element you're searching for with the first element in the linked list, and then the second one and the third one, and eventually with this element xi, and then you get a successful search, and you return a positive response that, or you return a true that the element is present in your linked list. So basically, what you need to do is find how many elements are there on the average before the ith element. So basically, let's assume for the moment that whenever you insert an element into the linked list, you insert it at the beginning of the linked list. So you compute the slot where the element has to be inserted, and then you insert it at the beginning of the linked list. And so what could have happened is you insert xi, and then you could insert xi plus 3 at some point, and then maybe you insert xi plus 9 at some point, and so on. And so the total number of elements that you insert after xi has been inserted is the length of this sublist before xi. So the amount of time it would take to return a positive or affirmative answer is the number of these elements, right? And so basically, we need to find out on the average how many elements are present here. Well, basically, the probability that any element xj is inserted into the same linked list as xi is 1 over m. So what you have is you're going to sum as j goes from I plus 1 to n of 1 over m. That's basically the average length of, that's the average number of elements here before xi. So the complexity of finding xi is, well, you have to, first of all, compare the element you're searching for with each of these elements, and then also compare it with xi, that's one more. And what you have to do, though, is this is for xi. What you need to do is average this over all the xi's. So you're going to be taking the average over all the I values, okay? And that's basically, this value here, by the way, is xij. It's the expected value of xij. It's the probability that the ith and the jth keys hash to the same slot. And so when you take this average, you basically do a 1 over n times the sum over I, right? That's how you take this average. And so that's basically what you end up with here, that the average number of elements examined in a successful search is, well, in a successful search for xi, first you have to go through a certain number of elements before xi in the same linked list where xi is, and then you got to basically there's a cost of 1 for comparing with xi itself, and then you take the average over all the I. So that expected value is the complexity of the search operation inside the linked list. And if you do the math, you can push in the expectation because of linearity. The expected value of xij is 1 over m. Well, you can see here that the sum of 1 multiplied by 1 over n is just 1. And 1 over n times 1 over m. The 1 over m comes outside. and you have the sum of 1 n minus I times, and so you get n minus I. Of course, the sum of all the n's is n squared. The sum of the sum of the first n natural numbers is n times n plus 1 over 2. What you get here is n squared minus n. Sorry, 2n squared minus n is n squared. So you get, for this parentheses here, you get n squared minus n over 2, which is n times n minus 1 over 2. And then this n here and this n here cancels, and you're left with n minus 1 over 2m. N over 2m is just alpha over 2 because n over m is alpha, and so you end up getting this. It's 1 plus alpha over 2. That kind of makes sense because if the on the average, the number of elements that you see here, if the average length of a linked list is alpha, then roughly approximately alpha over 2 elements would be present before xi. And so 1 plus alpha over 2 is roughly the complexity of searching through that linked list. And if you also wanted to compute the hash function, that's an extra 1. And so you get 2 plus alpha over 2 minus alpha over 2n. And so the total complexity of the search operation on the average is big theta of 1 plus alpha. So what this means is that if you can control the number of elements so that it's less than or equal to the number of slots, or at least if you can control the number of elements, n, so that it's big O of m, so it's at most some constant times the number of slots, right? The number of elements that you, so for example, if you take the constant to be 3, then, and you have 1,000 slots, and you can make sure that the number of elements you insert into these 1,000 slots is at most 3,000 always, then you know that the load factor is the constant 3. So in general, whatever the load factor is, if you can keep that load factor to a constant, then insertion, deletion, and search all take constant time on the average. So the main sort of conclusion of all this is that you can support all the dictionary operations in constant time on the average. So inserting, by the way, if you insert at the beginning of a linked list, can be done in constant time in the worst case, because to insert an element, you compute the hash value, which can be done in constant time, and then you can insert at the beginning of the linked list in constant time. So totally, it's constant time. If you want to delete an element and you're given only the key value, then what you have to do is first compute the hash function, and then you have to search for the element in a linked list. And that takes as much time as a search operation, which is big O of 1 on the average. And then once you find the location where you need to delete the element, you can delete it in constant time. Okay, so whenever, as you sort of traverse the linked list and you keep comparing the element you're searching for with the element in a linked list, you always maintain another pointer which trails the current cell, by by a unit of 1. So you always also maintain the address of the previous cell, and that way, once you find the location to delete, you can sort of redirect the pointer in the previous cell right away in constant time. So so delete can be done basically, delete has the same operation as search. So there's some practical issues with implementing hash tables because the issue is that we said that hash tables have a performance of big O of 1 on the average. That's really great. But that assumed that you can always maintain the load factor to be big O of 1. So if it turns out that you're inserting more and more elements into the hash table, and the load factor keeps increasing, then the performance of the hash table starts getting worse because the average length of a linked list keeps increasing. And what you could do is say, I don't know how many entries are going to be inserted into the hash table. So in order to ensure that the load factor is big O of 1, let me start off by allocating a really, really huge hash table in the beginning. But if you do that, you end up wasting a lot of space. What you want to do is somehow have the best of both worlds. You want to only allocate space on an as-needed basis so that you don't end up, wasting unused space. But at the same time, if you keep inserting more and more elements, you want to somehow do something so that the load factor doesn't keep on increasing. The issue is you don't know the number of elements that you're going to be inserting into the hash table in advance. So what you could do, and this method is sometimes called table doubling, is that when the load factor exceeds some given threshold, like say 50% or 2/3, for example, then you can go ahead and allocate a larger hash table. You can create a larger hash table and move all the elements from the old hash table to the new hash table using a new hash function, then that will reduce the load factor. So what you would do is initially you could choose a hash table T0 to contain some initial value M slots. So for example, I think in Python, a common value that M is chosen, this might be the case in Python, is M is equal to 8. Okay, so initially you go ahead and create a hash table with 8 slots. Let's say you want to maintain the hash table's load factor to be at 50%. So when you insert the first, second, third, and fourth element, they're inserted into this hash table T0. But now, when you insert the fifth element, what happens is that the load factor increases to more than 50%. It would increase to more than 50%. So what you would do is create a new table T1 containing 16 elements. So T1's size, okay, the number of slots in T1 would be twice the number of slots in T0. Obviously, you'll also need a new hash function, which would map to one of 16 slots rather than only one of 8 slots. And what you would do is you would take each of the 4 elements in the old hash table T0 and move them all to the new hash table by computing their hash values. Okay, and then you would insert the new element, the fifth element, into the new hash table T1. And then now T1 is a hash table with a load factor less than or equal to 50%, and you're okay. Once you start inserting the 9th element into the hash table T1, you go ahead and create a new hash table T2, you discard T1, and you repeat the process. So every time the load factor of a hash table increases to more than some threshold, like say 50%, you go ahead and copy all the elements from that hash table into a new hash table, which has twice the number of slots, and you discard the old hash table. Now, what is the complexity of doing all the insert operations? Suppose the first hash table had only 1 slot. I said earlier you can assume that it has 8 slots, but for the sake of this analysis, let's assume you're starting off with a hash table that contains 1 slot. So let T of n be the expected time to insert n elements into the hash table, where n is some power of 2. Let's say n is 2 to the k. Then to insert 2 to the k elements, what you have to do is insert all the 2 to the k elements into the present hash table. And that takes 2 to the k amount of time because every insert can be done in linear time. And then all the work that was done from the first hash table all the way up to the previous hash table that was just most recently discarded is T of 2 to the power k minus 1. So if you look at this recurrence relation, its solution is basically that T of n is 2n minus 1, which is big O of 1 for doing n operations. So if you take a linear amount of time to do n insert operations, it's big O of 1 per operation on the average. So so this table doubling business looks like it would really increase the cost a lot, but it doesn't. It basically only increases the cost by a factor of 2. So when you go from a hash table that has 4 slots to 8 slots, you might have to copy all the 4 slots over. And so eventually when you end up with a hash table containing 1024 elements, the number of different copying over that took place was 4 plus 8 plus 16 plus 32 all the way up to, let's say, 512, which is less than 1024. And so you have another 1024 operations being done in addition to the 1024 operations for inserting the element into the present hash table. So you have twice 1024 operations. So that's just a factor of 2 that's there, not a big deal. So so to summarize, if you don't know the number of elements that you'll be inserting into the hash table in advance, then you can still achieve big O of 1 average time per operation by basically using this method of table doubling, also called dynamic resizing. So one of the places where hash tables is used, if you're doing any coding in Python, is dictionaries. You might have used dictionaries in Python. So when you want to create a dictionary, you would say something like x of, so you would use actually curly braces. You would say x of 0, 0, 1, 7. In fact, in a dictionary, the key could be any mutable object. You could say x of ABC is the list 1, 3, and so on, and so this is a dictionary in Python, and dictionaries are really, they make a lot of the coding in Python really simple. I use them quite a bit, so a lot of my research is done using a lot of my research is in graph algorithms. And its applications in networking and data science, and a lot of this research I actually do the coding for it in Sage Math, which is a free open source software which is based on Python, and I use dictionaries quite a bit in my programming for my research. But anyway, the thing is that the way dictionaries are implemented in Python is using hash tables. Basically, once the number of occupied slots reaches about 2/3, that's the load factor, that's the threshold that's used for the load factor to decide whether or not to go to a larger table, then the hash table is doubled. I want to just kind of pause here. Any questions so far?
No, sir.
Any questions, for example, on the probabilistic analysis or the modeling assumptions here that was made either here to prove this particular value, or maybe in one of the earlier slides when I did the Professor Firoz, I think there's some background noise coming from your side.
Oh yeah, actually I noted for communicating to the participants. If you have any queries, you can please in the chat box also. Thank you.
Okay. So any questions, you can put them in the chat box as well, or you can feel free to speak up. So, I hope you see how in practice, for example, the way Python maintains dictionaries, how the average length of a linked list is kept bounded from above by a constant. Okay, the average length of a linked list is kept to be big O of 1 using dynamic resizing in this manner. And that way, as you keep inserting more and more elements into the hash table, the performance doesn't slow down. Okay, the operations don't take longer because the load factor is maintained to be a constant. So a lot of research goes into creating hash functions which do a good job of basically allotting keys randomly to the different slots. So you want to make sure that whatever hash function you're using is going to be performing well on your data. I mean, you don't know exactly what your data is going to be in advance, but regardless of what exact values are there in your data, your hash function must spread them out uniformly. Your hash function must spread out the data uniformly to the different slots, so that the average, so that if you insert n elements, into n slots, these n elements will all go into different slots with a high probability. Sometimes the keys might be a person's name or a string, okay, or some ID of an object, of an IoT device, for example, which could be a string. And the question is, if you don't have a student ID number as your key, but you have a person's name or some other string as your key, then you can't really use the numerical hash function. So these hash functions map. They're usually integer valued. Actually, I should say hash functions map usually from integers to the integers. They map from integers to a finite set of positive integers. What if your key is a string? For example, if the key is a string CLRS, how do you convert it into an integer? There's many ways to do it, but one way is to just say you're going to treat the string as a tuple of positive integers, where every element of the tuple is the ASCII code of that particular character in the string. So the letter A in the English alphabet has ASCII value 65. So C has ASCII value 67, L is 76, R is 82, and S is 83. And since every one of the if you're using the 128 basic ASCII values, then each of these ASCII values goes from 0 to 127. So what you really have here is a number in base 128. In general, a number in base B will have every one of its digits being from 0 to B minus 1. And there's a standard method to convert from base B to base 10. What you do is you multiply each of these digits by the corresponding power of the base, and you get the base 10 representation of that particular base B number. So you can convert from base 128 to base 10, and then now this is a unique integer. So every string will have its own unique integer representation if you do this, because any two different base 128 numbers will have different base 10 values. And from here, you can go ahead and use the usual hash function to get the slot. So a lot of research work has been done. A lot of probabilistic analysis has been done to analyze the performance of these hash functions. I won't be getting into that too much. Yeah, I think open addressing, I mean, it's, yeah, let me talk about open addressing as well. Basically, in open addressing, instead of, so another way to store the elements into a hash table is instead of having linked lists external to the initial array, you can store the elements in the array itself. Of course, we saw this in the beginning. If you use direct addressing, you can do that, but you have to allocate a whole lot of memory in the beginning, and that's not practically feasible. So another option is to allocate a small array rather than a really large one that's the size of the universe, and use a hash function. Of course, you can have collisions happening, and then we have to talk about how to deal with collisions. In linear probing, what you do is you create an array of, let's say, m slots, where you would actually store the data itself. So these arrays are not just pointers, but they would actually contain the data. And when you're given a key k, you go to hash, you compute the hash value h of k. And if that particular slot number h of k already has data in it, then you basically probe the next slot, which is slot number h of k plus 1 of the table. And if that slot is empty, then you insert the key right there. Otherwise, you probe the next slot, and so on. Once you reach the end of the hash table, meaning once you reach the last index, you start at the first index, and you continue. So you kind of wrap around. So when you look at the indices in this array, they're basically computed mod m, modulo m. Basically, you take the remainder mod m. So if you wanted to, for example, insert the following items into a hash table, where you have 10 slots, let's say 0 to 9, then, and if the hash function h of k was k mod 10, then 37 goes obviously into slot number 7, 13 goes into slot number 3, 14 into slot number 4, 9 into slot number 9. The problem is if 23 has to be inserted into, 23 is supposed to go into slot number 3, but there's a collision there. So you examine the next slot, which is slot number 4. That's also filled up. And so you insert 23 into slot number 5. 16 can go into slot number 6. 8 can go into slot number 8. 7 has to go into not slot number 7, 8, or 9, but 0. And finally, 3 has to go not into slot number 3 or 4 or 5 or 6 or 7 or 8 or 9 or 0, but right there. So this is, you know, there are other ways to do this. Here, the probe sequence was, you know, h of k. It was slot number h of k plus 1, h of k plus 2, and so on until an empty slot is found. There's other possible ways to do it. You can have basically h of k comma 1, h of k comma 2, h of k comma 3, and so on, where h of k comma j is some function of h and j. So the set of values that you get, so if you basically take all the different if you take m different values, if you take m consecutive values of j from 1 to m, then this set is basically going to give you all the different slots. In other words, this sequence h of k1, h of k2, all the way to h of k comma m is a permutation of the set 0, 1, 2 to m minus 1. And there are many different functions you can use. In this particular example of linear probing, h of k comma j was just h of k plus j, maybe a minus 1, right? But there are other different functions, more complicated functions as well. And they all have different, you can analyze them mathematically again for their performance. So if you want to look at the performance of some of these hash functions, you can look at the text, the CLRS textbook. So the advantages of using such linear probing schemes is that you don't waste a lot of extra space on pointers like you would do if you're using if you're resolving collisions using chaining. On the other hand, you really do have to know at the beginning itself how large your array should be, and you can never store more elements than that. That's a standard sort of advantage that our linked lists have over arrays, which is that in linked lists you don't have to know at compile time how many elements you'll be storing. One disadvantage of linear probing is that you can have long runs of consecutive occupied slots, and that would basically reduce the performance of the operations on the hash table. So I kind of want to end right here. Let me just sort of tell you, I mean, I like to empower my audience and the participants with where I got the material from, so that if you want to sort of learn more on this stuff, or if you want to read about it more slowly at your own pace, you can go ahead and do that. So reading books is a great way. Spending time to sit down and work through exercises in the books and reading the books is a great way to improve your understanding. And here's where I got the material from. The analysis of hash tables with chaining was obtained from CLRS. I guess I used Python, but if you sort of want to look at a really good introduction to programming and Python, I think many of you might have done programming in C++ or Java, but I think Python is a really wonderful language, and if you want to sort of get into Python, I think this is a really good source. It's also available on I think it's 6.0001 on MIT OpenCourseware, and actually one of the programs that I gave today on how to implement hash tables in Python, where you had a list of 10 sublists, right? That was from the GutTag textbook, which is a really great book. I kind of like programming books which emphasize computational thinking and problem solving rather than just the syntax of the programming language. So a lot of Python books, they just talk about the syntax of Python, like how do you do a for loop or a while loop? How is it different in Python compared to other languages? And so you end up learning the syntax. But I mean, it's always better to use books which emphasize, how do you take a real world algorithmic problem and convert it into a solution which you can solve with the help of a computer. So how to think computationally. So there's a lot of algorithms and mathematics that's used, and very minimal syntax of Python itself is introduced in this book. So I think this is a really great book. And that's the one that I actually use when I teach Introduction to Programming. I know you all have, I think many of you would know Python, but I think often, I mean, I meet a lot of programmers who've done Java and C++ and haven't yet migrated to Python. So I'm just giving you these two references. Of course, we talked about hash tables, a bit in the context of Python, for example, uses hash tables when it implements dictionaries. So, we've talked a bit about, applications in big data. But if you really want to sort of, this would take more time, a lot of time. So we don't have time to get into that today. But if you want to, like, look at a good algorithmic resource for a good resource on data mining, which sort of has a very sort of which takes an algorithmic view of the field, then this textbook, Mining Massive Data Sets, is a really good one. And hash functions show up all over the place. Streaming applications, social network analysis, frequent item sets, and other big data problems all use hash functions one way or another. So if you want to look at applications of hash functions, you can actually just do a keyword search for the word hash in this book, and you'll find lots of them. I just want to quickly end. This is a little bit of maybe advertising. INSOFE, the International School of Engineering, our institute, we're starting many doctoral programs in data science. We have a doctoral program with the Rennes School of Business in France. You can look at our website to learn more about it. So we're also starting doctoral programs in other places, for example, a PhD in data science at Vijay Bhumi University, which is in Maharashtra, and this is a fully funded PhD program. So you can look at our website and contact the appropriate people there or call them up if you're interested in getting a brochure or learning more about our programs. So you'll have the opportunity to do research work and also publish papers. INSOFE is based in Hyderabad. That's where the primary base is, but we also have offices in Bangalore and Mumbai. That's all I have for today. Any questions? So, I didn't get, maybe I could give another lecture later on, like maybe a research-based a lecture. I think in general, in faculty development programs, last time, by the way, I think for those of you who came to my talk about a month or so ago, it was more of a research-based lecture where I presented a research paper and how you could possibly extend it. I looked at the Gervin-Newman algorithm for detecting communities and social networks. Today, I talked about something which is probably traditionally covered in bachelor's and master's programs in computer science, hash functions. But hopefully, I covered it more rigorously, and hopefully, when you teach that same material in the future yourself, you can do a combination of both doing something which is mathematically rigorous and which is also applied. So you can illustrate some real-world applications of where hash tables are actually used. In this case, I gave Python because a lot of people use Python today, especially dictionaries in Python. But there's many other applications. Maybe I could talk about that some other time. Any questions on this material that I covered today?
Participants, now you please put your queries. As I mentioned earlier, you can give your questions in the chat box also. Yes, Professor Ashwin, I feel there is no questions from the participants. So we have recorded this video. It was indeed a very wonderful lecture we have given. Even for me, it was, I find it very much resourceful and useful. So the videos will be sharing to the participants also. And so if you can please share the slides to us, that also will be given to the participant.
Sure,
and,
I'll do that.
Yes, a recorded video will be shared to you as well, sir.
Great, thank you.
So thank you, Dr. Ashwin. So we'll meet again probably in the next training program also we can.
Sure, yeah. It was a pleasure to give the talk. We'll be in touch. Yeah.
Yes, thank you so much, sir. So dear participants, now we will have our second session talk in 10 minutes. So please be here. Our resource person will be joining very soon. Thank you so much. Hello all, welcome back to the program. So now we'll be starting our second session. Our resource person has joined, Dr. Vibhor Kant. I guess you can hear me.
Yes, sir.
Okay, so thank you so much, sir, for joining. Dear participants, now we have with us is Dr. Vibhor Kant from Banaras Hindu University. So he'll be giving a talk on hard and soft support vector machines with kernel methods and their applications. So before going to the technical session, I will give a brief introduction about Dr. Vibhor once again. Okay, thank you so much.
Good morning, Professor Vibhor Kant sir, and all the participants. We are glad to have you here in our short-term training program on second phase Big Data Analytics. I would like to introduce Professor Vibhor Kant sir to our participants briefly. So, Dr. Vibhor Kant sir is currently associated with the Department of Computer Science at RGSC Unit of Banaras Hindu University, Varanasi. Prior to joining DAY2, he had served as an assistant professor in the Department of CSC, Computer Science and Engineering at the LNMIIT Jaipur. He had also worked as an assistant professor in the Department of CS at Kalindi College, Delhi University. He had also served as lecturer in the Department of Mathematics at KAPG College of Dr. B.R. Ambedkar University, Agra. Dr. Vibhor Kant has earned his MTech and PhD degree from JNU, New Delhi, after completing his MSc in mathematics. He has guided various undergraduate and postgraduate students for their projects and dissertations. He has also supervised two PhD students. He has published various articles in SCI, SCIE, Scopus Index reputed journals, and conferences proceeding. With this, I would like to welcome Dr. Vibhor Kant sir. Over to
Thank
you.
you, sir. Thank you, sir. Am I audible?
Yes, sir.
Okay, thank you, sir. So, I'm sharing my slides. Is slide visible?
Yes, sir. Visible.
Okay. So thank you for the nice introduction. So in this talk, today I will go to present support vector machine with two variants, hard and soft. We will discuss in this talk how to formulate mathematically and their applications I will discuss. If time permits, then we will go for some demonstration as well. So this is the outline of my talk in which I will discuss what is the history of support vector machine and two important cases, linearly separable, which is related to hard SVM. And second one is non-linearly separable, where we can use soft SVM as well as kernel methods. And we will discuss some example and some discussions and conclusion. So before discussing support vector machine, I want to tell you it is a very good a tool for the machine learning task. So generally machine learning task can be categorized into three categories: supervised learning, unsupervised learning, and reinforcement learning. So whenever we will discuss supervised learning, so two important aspects regarding supervised learning, a classification as well as regression. So both can be done by supervised learning. So there are a lot of algorithms available, tools available, which can do these two tasks or which can do supervised learning. So you can, I think, decision tree induction, Bayesian classifier, support vector machine, artificial neural network. So these are the very popular algorithm or tools in machine learning, which can deal data science or large data as well as small data as well. So support vector machine generally related to supervised learning. So in supervised learning, there are lots of applications, just like hand character recognition, face recognitions, recommender systems, and lots of. So we will discuss first what is classification problem. Then we will go further. So suppose for any data science task or machine learning task, data is required. So classification data, in which a data is represented by so many attributes, and these attributes are the features of a particular object. For example, suppose we want to classify a person into two categories, male and female. So male attributes and female attributes will be there, and last attribute can be seen as the target attribute. So in the last attribute is decision discrete or decision attribute, or it is discrete one, because male and female, there are two class. So such data is referred to classification task, which is related to supervised learning. Similarly, regression task, what is the difference between the classification data and regression data? In the regression data, the last decision attribute can be continuous, just like a stock market price prediction. Okay, so the market price can be in continuous range. So which is related to regression problem. So these two problems, classification problems as well as regression problems, are into the category of supervised learning. So this is the simple introduction regarding the classification and regression. So we will discuss support vector machine for the classification task or supervised learning task. So I want to tell you, whenever machine learning has been started, so there is a very famous scientist you can see in this third reference, Vapnik. Vapnik has introduced a statistical learning theory, in which they have categorized some important aspects for machine learning, which can provide some foundation for the learning algorithms. So support vector machine is has some idea regarding some concept regarding statistical learning. So it was firstly introduced in this reference, Bozer et al., where it has been introduced. So we will discuss the idea about support vector machine with the reference 1. It has been popular when the success rate to a handwritten digit recognition as compared to constructed neural network, carefully constructed neural network, which has in comparison to this neural network, the support vector machine has achieved more accuracy in comparison to this neural network, LeNet4. So it has been popular initially. So after the introduction of support vector machine, initially the support vector machine has been designed for the linearly separable classes, and it has been further extended non-linearly separable classes, in which kernel techniques will be discussed. So we will start a very simple thing, starting with hard SVM. So in hard SVM, we can take one simple example in this figure, and these slides are taken from the data mining book Vipin Kumar. So in this you can see these are the objects, red circle and green square. So in the data set there are some objects, and these objects has two categories, red circle and green square. Means in the last attribute, which I told earlier, decision attribute can be seen into two discrete labels, red circle and green square. So data set is given to us. Now we have to train our classifier which can deal classification problem. So question arises, am I able to draw a line which can separate these two classes of object? This is very simple one. because linear, I am just telling it, am I able to draw a linear line, or linear line means a linear hyperplane in 2 dimension. So am I able to draw a line? Am I audible? Hello?
Yes, sir, you're
Yes, sir.
audible.
Okay. So I'm saying that, am I able?
Yes, sir.
Yes, you can see, yes. So you can see I have drawn a line, or we can say in more general, it is a linear hyperplane or hyperplane in more dimension. In 2 dimension, it is simply line. So am I able to draw a line? So line can separate these two objects into two different categories, in red circle and green square. So which now second question, this is also B2 is also a second line, okay, which can also separate these objects into two categories. So question arises, which one is better? Initially, I want to tell you some introduction. Initially, artificial neural networks tries to draw such a hyperplane by using perceptron learning. But in that perceptron learning, it is not guaranteed which one is better. So in this discussion, I had drawn the first one B1 and second one is B2. So question arises, which one is better and which one is optimal? So these two ones, question arises, which one is better? So I want to tell you important point, which is the foundation for support vector machine. So you can see here, to decide which is better, we will draw a parallel hyperplane with the decision boundary. So first of all, we are focusing the first decision boundary B1. So this is the B1 boundary, and we are drawing the parallel hyperplane with respect to closer corresponding classes. So this one is the closer to red circle, which is a parallel to B1. Similarly, the second one here, this one, so which is a closer to a green square. So we have drawn the parallel hyperplane with respect to decision boundary B1. Similarly, we will do the same exercise for the B2 decision boundary. So we have got this one parallel hyperplane and this is second parallel hyperplane. So the basic foundation for the support vector machine is the distance between these two parallel hyperplane is higher. Which one? That one is would be the better. This is the foundation. So you can see this is the distance between the parallel hyperplane with respect to B1. Similarly, you can see in this one with respect to B2. So this is called a margin. So a margin will be higher. Corresponding decision boundary will be optimal. This is the foundation for the support vector machine. So based on this concept, we can say B1 is better because the margin with respect to B1 decision boundary is higher in comparison to B2. So B1 is optimal one. So this idea will be captured in the mathematical foundation for support vector machine. So as I told, data set is required for training any classification algorithm. So in these slides, you can see what are the bad decision boundary. This is bad decision boundary as per previous discussion. This one is a bad decision boundary as per the previous discussion. So as I told, margin should be the higher or margin should be the maximize. So we are dealing with margin. So support vector machine or hard support vector machine, why it is called hard? Hard means you can see here, we are not allowing any objects in this margin. You can see in this figure, in any margin, there is no object. So that's why it is hard. So we are discussing first mathematical formulation for hard SVM. So in hard SVM, and you can see this is an optimization problem. in optimization problem, there are two major components. The first one is objective function, and second one is constants. So question arises how to formulate objective function and how to form constants. So these can be done with the help of data sets. So as I told, margin should be maximized. So objective function will be formed with this idea, margin should be maximized. So I am discussing how to formulate optimization problem for hard SVM. So you can see, suppose this is the B1 or this is the decision boundary, and these are the corresponding hyperplane, and this is margin. In 2-dimension, you can see these are the lines. So for the simplicity, I am taking general equation of line WTX plus B is equal to 0. It is very similar to your high school standard line equation AX plus BY plus C equals to 0. And you can put here A comma B and X comma Y plus C equals 0. So that is W transpose, and this is X, and this is constant. So you can visualize in this fashion. So WTX plus B is the decision boundary which I am taking, and we have to train our support vector machine to maximize this margin, in which we will get optimal W. So WTX plus B. So corresponding, we are taking parallel hyperlines. So as you know, in the 10th class label, parallel line equation AX plus BY plus lambda. So in this fashion, just difference between the constant terms. So for the simplicity, I am taking here differentiating only the constant term. B in place of B minus 1. Similarly, in place B or B plus 1. So we have framed two parallel lines. Minus 1 or plus 1 I am taking intuitively, because we will discuss data sets into two categories. The first category can be seen as the plus 1 category, and second category can be seen as the minus 1 category. So red square can be seen as the minus 1 category objects, and green circle can be seen in the plus 1 category. So I can say, if a green circle can be classified by this parallel line WTX plus B equals 1, means greater than equal to 1. So all these objects which are satisfying this parallel hyperplane WTX plus B greater than equal to 1 will belong to the class label plus 1. Similarly, for the red square, we can say all the objects which are satisfying the second parallel line WTX plus B less than equal to minus 1, then we can say all the objects will belong to the class minus 1. So our object is what is the margin, because we have to form objective function first. So what is the margin? So margin can be computed with the help of perpendicular distance between these two parallel hyperplanes. So perpendicular distance from origin, this one and this one. Okay, distance between these two parallel hyperplane, we will get the margin. So after what is the perpendicular distance? AX plus BY plus C equal to 0. You have read in 10th class, A square plus B square. Clear? So similarly, we can compute the perpendicular distance for this hyperplane B minus 1 upon, or under root A square plus B square, just like a norm W. W1 square plus W2 square. Similarly, for the second one, which will be B plus 1 upon norm W. So distance between these two will be the margin. So after subtracting, you will get 2 upon. Distance cannot be negative. So margin can be seen in this discussion 2 over W. So the margin should be maximized. So we have to maximize this one. So this will be the objective function. So now how to form constants. So in this figure, you can see we have taken some examples, which are the data set. So now mathematically we will decide, suppose the data set x1, x or n. So these are the n objects in the data set, and these objects are categorized into two categories, which is the categories are represented by yi, and it will take only two values, +1 or -1. As per our previous discussion, green circle is belonging to +1 and red square is belonging to -1. So that's why I am taking +1 and -1. So x1 will belong to either +1 or -1. It will be fixed, but I don't know x1 is belonging to +1 or -1. I don't know. So if data set is available, then we can say, yeah, I know. But to form a mathematical formulation for the constants, we will take both the cases. So we will take the first object, suppose x1, and I am taking the first case. Suppose x1 is belonging to class 1. So x1 is belonging to class 1. What will happen? It will satisfy the upper hyperplane wtx plus b greater than equal to 1. So x1 will satisfy wtx1 plus b greater than equal to 1. Clear? So now I will multiply both sides by y1 because x1 class label is y1. I don't know what is the value of y1. I have taken the first case, y1 is belonging to +1, so y1 value is +1. So I will multiply both sides y1. So what will happen? y1 wtx1 plus b greater than equal to y1. Okay, so y1 value is +1 because I have assumed x1 is belonging to class label 1, so it will be +1. So you will get y1 wt x1 plus b greater than equal to +1. You can second case we can take also case 2, where I will assume x1 will belong to second class label, which is -1. Means y1's value is -1. So suppose x1 is belonging to the class label -1, then definitely it will satisfy the lower hyperplane wtx plus b less than equal to -1, as I told earlier. So we will take that one, wtx1 plus b less than equal to -1. Again, we will multiply by y1 both sides. Here y1's value is -1. It is inequality form. Y1's value is -1. That's why inequality will be changed. So y1 wtx1 plus b greater than equal to y1's value is negative -1. So inequality will be changed. -1 will be +1. On the right hand side, I am putting the value. So you can see in both the cases, you are getting the same constant with respect to the first object which I have taken x1. So we can frame or we can form other constants as well by taking x2 object, by taking xn object. So by taking the second object, we will get the second constant y2 wtx2 plus b greater than equal to 1. By taking nth object, we will get the nth constant yn wtxn plus b greater than equal to 1. So we are generalizing by taking the index I. So yi wtxi plus b greater than equal to 1 for every I. So we have got n constants with respect to every object by taking both categories one by one, and we are getting the same constants. So these are the constant, n objects, n constants. Now objective function, as I told earlier, we have to maximize this one. Norm W means length of the vector, means square root of a square plus b square. Suppose W is represented by W1, W2, then it will be square root of W1 square plus W2 square. So we have to maximize this one. So object rather maximize, we are focusing on the minimize. So we can just reciprocal it and taking square, because the square root can be difficult to differentiate. That's why we are taking square. So minimize half W square. This will be the objective function which can be based on the margin. In margin should be maximized 2 over W. Okay, norm W. So I am taking for the simplicity 1 by 2 norm W square. And these are the constants. So this is the mathematical formulation for hard SVM. This is known as primal form of hard SVM. Mathematically, we can say this is the constant optimization problem in which objective function is quadratic. So it is a quadratic programming problem. And how to solve, because initially we have started support vector machine, which has the idea about the statistical learning theory. So we have to solve this optimization problem. So I am just taking some recap of how to solve optimization problem, and someone knows how to solve this quadratic program problem and someone don't have idea. So that's why I am taking some slide. Suppose this is the objective function which is should be minimized, and this is only one constant which is equality form. So for solving optimization problem, we will form first Lagrangian. Lagrangian will be formed with the help of objective function as well as the constants. And because only one constant which is equality form, so lambda gx or alpha gx, in this slide alpha gx. So this is the Lagrangian. So Lagrangian should be differentiated with respect to x as well as with respect to alpha. So after differentiating with respect to x, I have put here that is Lagrangian. I am putting it equal to 0 to find out the stationary point. And after differentiating with respect to alpha, you will get gx. So gx is equal to 0. Here alpha is Lagrangian multiplier, which is unrestricted in sign. It can be negative or positive for the equality constants. We can extend, there are so many constants of equality form, gix, suppose m constants, then or n constants. So I will add corresponding Lagrangian multiplier and we will differentiate with respect to x as well as every Lagrangian multiplier. You will get the stationary point after solving this. So this is the idea about the constant optimization problem where constants are equality form. But you can see our primal form, the constants are greater than equal to or inequality form. So I'm just extending it how to deal with inequality constants. So I'm taking the less than equal to type, gix less than equal to 0. Same concept will be used. First of all, we will make Lagrangian multiplier and differentiate with respect to x, and with respect to alpha I, you will get the same thing. But what is the difference between the previous equality form or inequality form? In the equality form, I have told you alpha is unrestricted in sign. Here alpha I will be non-negative. This is a difference between the inequality form or equality form. Inequality I am taking here less than equal to type. So we will use this idea to solve primal form of hard SVM. So now I am coming back the primal form, which is half W square. And because I have introduced inequality as the less than equal to form, less than equal to 0, that's why I have framed, I have just changed some, slightly changed. We have transferred the left hand side here and we will get the less than equal to 0. So you will get 1 minus yi wtxi plus b less than or equal to 0. I belongs to 1 to n. So now we will make the Lagrangian. So Lagrangian will be half w square, norm of w square can be written as wtw in matrix form, plus alpha I 1 minus f. For every constants I have used Lagrangian multiplier. Here alpha I will be non-negative. Now we will differentiate with respect to w with respect to alpha I. So after differentiating with respect to w, this Lagrangian function, we will get w square means 2w. So 2 will be cancelled out. That is the reason I have taken only 1 by 2. And here the first term will be 0, and alpha I, yi, and w transpose you can see less w. After differentiating with respect to w, you will get 1. Same thing you will get here. Similarly, bi term will be 0. So I have got, after putting it equal to 0, I have got w value. And second one is differentiating with respect to b. B is also another parameter. Here we will partially differentiate with respect to b. You will get a second one. And we can also differentiate with respect to every alpha. You will get the same constants. This one. So w I have got, which is important one. So this is the idea how to solve primal form of hard SVM. Now, question and the important point is in support vector machine is the dual form. So question arises how to form dual optimization problem from primal. So I want to tell you, because I have got W, this is the one solution. So W can be put into the Lagrangian function. Okay, you will get dual. I am putting W in the Lagrangian L. So after putting W transpose, same value will be put two times in the transpose form. Here the transpose form. And I am using alpha I, yi will be 0. Okay, so that will be put here 0. Clear? So after putting all these things, you will get, this is the dual. So dual can be formed with the help of W and Lagrangian function. So this is the dual form of hard SVM. And note that means it is also given to us with respect to the partial differentiation with respect to B. So this is another point. So after this is maximization. If the primal is of maximization, then dual will be for minimization. So the primal
Dear participants, it seems some network issue.
Sir is
Totally,
not audible. Sir is not audible, sir.
is it audible now? Dear participants,
It's not audible.
Participants, there is some network issue going on, so it will be solved very soon. So please be here, please don't leave.
Just now. Okay, okay. Okay, 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 okay. Come back. Hello, everyone.
Yes, sir.
So please tell me where we are. We were. Hello.
Yes,
Am I
sir.
audible?
Yes, sir. Yes, sir.
And the screen is visible.
Yes, sir.
Okay. So please repeat where we have stopped.
Slide 15.
Yeah.
Right, 15.
Yes, sir.
Yes.
Slide number 15.
Dual.
Okay.
So
Yes,
we
sir.
are discussing dual problem, sir.
Okay, okay. So this one. Is it
Yes, sir.
clear?
Yes, sir.
Yes, sir.
Okay. So in the discussion of the dual form of the hard SVM, so you can see this is the dual objective function. So the relationship between the primal and the dual, if the objective function of primal is minimization, then definitely dual objective function for maximization. And dual primal constants will provide dual variables. So, and also you can see in the dual objective function, only alpha i's are the parameters, because yi, yj, and xi transport and xa, these are these are coming from data sets. As I told, xi and x1, x2, xn are the data objects. So these are the constants which are given to us. So only parameter are alpha I. So, and also these objects are appearing in the inner product form. I will discuss what is the importance of inner product in coming slide. So just you can see maximization, as I told, dual is primal is minimization, then dual will be maximization. So this is maximization, and this is non-negative. As I told earlier, alpha I will be non-negative, and this is the second one, alpha I, yi 0. So, and another important relationship is, if we know W, then we can compute all alpha I. And if we know all alpha I, then we can compute W also, because the relationship between the solutions. So as I the solution of primal, W can be recovered alpha I, yi, xi. So yi, xi can be appeared from the data set. It is given to us. So if we know alpha I, then we can compute W. If we know W, then we can compute alpha I. So that is another relationship between the solutions of dual solution as well as primal solution. And am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
So I
Yes,
have
sir. Yes,
already
sir.
told about the importance of support vector machine is in comparison to artificial neural network. I have started with how to draw a linear boundary with respect to artificial neural network that can be trained by perceptron learning as well. But perceptron learning does not provide any guarantee of optimality. Here I can say, with the help of objective function of the primal hard SVM, we can provide the guarantee of optimality. The reason behind is the primal form has objective function half W square. This is the convex function. So because of the minimization problem, convexity of the objective function provide the guarantee. So that's why support vector machine has achieved greater consideration till now. So as this is the slide 17, I told this one, global optimality. Now I want to tell you regarding the big data concept or large scale machine learning. So if the data set objects are very large, n is very large. As I told, I have started x1 and xn. Okay, so n is very large. So that is a scalability problem. So in support vector machine, if n is very large, that I can say support vector machine handle the scalability problem efficiently. How? As you remember, when I forming constants, I have taken every object and corresponding I have framed one constant, just like wt x1 plus b or y1 greater than or equal to 1. And when I am making Lagrangian, I have used corresponding alpha 1. So for every object, we have got alpha 1. For every object, if n is very large, then alpha 1, alpha n, all these are very large. N is very large, then Lagrangian multiplier are very large. So listen carefully. After solving optimization problem, you will get, if n is very large, you will see when you will deal the real problem, you will see definitely most of the alpha i's are very zero. Most of the alpha I. Suppose n is 1 million, then you will get approximately 50,000 or 1 lakh will be zero, or 1.5 lakh will be zero, or 9 lakh will be zero. So what is the meaning of this? I am just relating every object with respect to alpha, because x1 alpha 1, xn alpha n. If alpha I will be, most of the alpha i's will be zero in the scalability issues, then what will happen? We will focus only on those alpha i's which are non-zero. Okay, which are non-zero. So corresponding vectors, just like if alpha 1 is non-zero, then corresponding data object is x1. So if most of the alpha i's are zero, means very few alpha i's are non-zero. So very few data objects you will get. So these objects which are corresponding alpha i's are non-zero, these objects are called support vectors. So you can see, because our target is how to find out W. W is important point. We have to find out the optimal W. So you can see here, just see this one, W can be recovered with the help of alpha I. So most of the alpha i's are zero. Then some of the alpha i's are non-zero. So we are taking that set, or corresponding objects will be the support vectors. So we are taking Tj be the indices of the support vectors, and we can write. There is no need to write other terms because all corresponding alpha i's are zero. So alpha Tj, Ytj, and Xtj. So if the n is very large, we are using very few objects. That's why support vector machine deals scalability problem efficiently. So after getting support vectors, we can classify new data as well. When it is a general overview of classification problem, we suppose data set is given to us, then we will divide our data set into 2 or 3 categories: the training data set and test data set. Suppose 2 categories. So training data set will be used to train the machine learning algorithm, and test data will be used as a future data. So I'm saying that suppose a future data is Z, then how to classify? So we will use WTZ, decision boundary we will use. So WTZ plus B, and I'm putting the value of W, which is the linear combination of support vectors. You will get this one plus B. So after solving this one, if it is greater than 0, positive 1, then it will belong to class 1. Otherwise, it will belong to class -1. We are using here decision boundary. Clear? So this is the idea about, complete idea about the hard SVM. Why I have discussed the mathematical formulation. Currently Python libraries are available, but students and other learners, and some students, some are learners, does not know how to, what is the foundation behind it. That's why I have discussed those ones. Now, These are the tools for solving support vector machine. I am just skipping slide number 19. So as a mathematically, geometrically interpretation, as I told earlier, support vectors. So these are the support vectors. Corresponding alpha i's will be non-zero. And all other alpha i's, because for every other remaining object, you will get all the, this is the geometrical interpretation. So this is the hard SVM. Out of 10 or 12 objects, you are getting only 3 support vectors. For a small data, there is no need, but for the large data, you will get most of the alpha i's at 0. Now I will introduce some softness in the hard SVM. Means we can allow some flexibility in the margin form. I have assumed initially there will be no object in margin space. Clear? Here I am allowing space, here I am allowing some flexibility. Some objects can be in the margin as well. So that is the soft SVM. So that margin can be seen as an error in comparison to hard SVM. In hard SVM, we are not allowing, but in soft SVM, we are allowing. So you can see, you can visualize just like an error. So I have started with data set x1, xn. Just remember the previous discussion. So I am just saying every example has some error. X1 has some error means xi1 and xin. Every example has some error in the soft SVM. So our target should be, error should be minimized, margin should be maximized, and error should be minimized. So this idea can be used to form primal as well as dual of soft SVM. And same thing will be repeated. So as you, I think you remember, in the primal form of hard SVM, you have seen only one objective. In the only one term in objective function, half W square. Here I am adding error term for every object because there are n objects in the data set. That's why I have allowed every object some error. So xi1, xi2, xin, and I am adding complete error I have got after adding those one, and this is the trade-off parameter. So I will discuss how to decide trade-off parameter. So this trade-off parameter will be decided by empirically. There is no hard rule, but how to form constants. This is important point. Because objective function is simple. As I told in this discussion, we have to minimize the errors. So I have added one extra term here. Some of those errors and corresponding trade-off parameter C. I am using trade-off parameter. I will discuss later. But how to form the constants? Suppose with respect to positive examples, means a green circle. So it will be in the margin. So what is happening? Suppose it is in the middle. Suppose decision boundary is in the middle and this is 2 over W as you remember. And this is plus1. So I am saying that it is coming to in the margin, then definitely it will be less than 1 minus xi1 or xi2. WT, this hyperplane will be here. Similarly, this parallel hyperplane will be here. So it will be adding something with respect to the origin. We are coming closer to origin. That's why 1 minus. With respect to second one, we are going further. Then we can add that corresponding error in this one. So we are using this idea. For the positive class, we are using this one. For the negative class, we are adding. As you remember, by taking both cases, you are getting the same constants. So constant will be like this. Same thing you can use, suppose class 1. Then you will multiply y1. This is 1. Y1, because y1 class level plus 1. Then you will, there is no change. But y1 class level minus 1, then definitely it will be changed. And 1 minus 1 will be plus 1, and that is minus 1. So you will get the same constant. So constants can be formed in this form in soft SVM. This is the primal form of soft SVM. where we have allowed some errors in the margin. Why it is called trade-off parameter? If we are allowing some errors, then margin will be decreased definitely. So that's why it is called trade-off parameter. I initially I have started, we have to maximize this margin. After introducing some errors, we have to, margin will be lesser. So that's why it is called a trade-off parameter. That's why we will decide through empirically after taking C's values starting from 5, 10, non-negative parameter 10, 15. We will check the results, then we can take the optimal value of C. So that is the idea how to decide C value. So as I told previously, how to solve diagonal form, just make the Lagrangian and differentiate partially. And after differentiating partially, you will get W, and that W will be put into the Lagrangian, you will get the dual form. So I am not telling that one. So directly I am telling the dual form of soft SVM is same, objective function will be the same, only one change. Second, these are the constants, and only one change. In the hard SVM, alpha I are non-negative. It is also here, but alpha I has the maximum limit, which is referred to as C, which is, and similarly you can recover. So after solving the dual form, you will get so many alpha i's, and all the alpha i's, most of the alpha i's will be 0, and some of the alpha i's are non-zero. So corresponding data objects can be seen as the support vectors, and other terms will be 0 because of the non-zero alpha I. So we are taking only those support vectors form. So same thing will be here. Only one change in the dual form of soft SVM. Lagrangian multiplier has the upper bound, which is C here. So any problem till now? Till now we have not introduced kernel tricks. And after this we will introduce kernel methods as well. So is there any query? Hello? Hello, am I audible?
Yes, sir, you're audible.
So I'm just asking if you have any query regarding hard SVM as well as soft SVM, then please ask. If you have no query, then we will go further. Hello?
Dear participants, as I mentioned earlier, please put your questions in between in the chat box also, so that in the meantime, the first person will be seeing that, and he'll be answering for that also. So please do that. And if you have any question now, I can ask now.
No. Okay. Now I want to tell you how to deal non-linearly separable cases. Non-linearly separable. I have started with the linearly separable cases. So before telling some written text, I want to telling you a very simple way. Suppose the objects are given in this form. So I am not able to draw a line or hyperplane. So how to deal such cases? So idea is very simple idea. If we are able to transform our data objects into higher dimension, initial dimension can be referred to input space. After transforming data objects into higher dimension, we will say feature space. So transformation function is given to us phi I, and every data point has been transferred into higher dimension. For the visualizing perspective, I am using 2 dimension. In higher dimension, I can assume the data set, the objects will be linearly separable. But computation of the feature space, because initially 2 dimensions, suppose data set input space 2 dimensions, so every object will be represented by 2 features, F1 and F2. If we are transforming into higher dimension, suppose 10 features, then every object will be represented in higher dimension. So as you see here in the mathematical dual form, the data objects are appearing into inner product form. If in lower dimension, definitely, you know, a vector A, suppose A1, A2, and vector B is B1, B2, then what is A dot A transpose B or A dot B? A1, B1, A2, B2. So you are multiplying two multiplicative operations. Suppose we are transforming our data objects into higher dimension, what will happen? That computational complexity will increase. So this is another point which should be discussed in the transforming our data into higher dimension. So question arises, why in higher dimension can provide linear separability? That is important point. First point I want to tell you, why in higher dimension linear separability will occur. That can be discussed intuitively here. Suppose I am taking this example. These are the data objects. Red circle and blue square. I am not able to draw a line, but you can see the circle can classify these objects into two categories. And suppose this circle center is plus 1.5 or minus 0.5 in this figure. So corresponding equation like this, and this will be the radius 0.02, 0.2 or 0.04. So if so based on that you can classify. So after solving this equation, you will get these the two space x1, x2, and this circle equation can be written in this fashion: x1 square, x2 square, after and some constant square, and some 2x1 and 2x2. This will be 2 cancelled out. So x1 square minus x1. Similarly, x2 square minus x2. I am ignoring the constant square here. So you can see what is happening. Initially, only two features, x1, x2. But in the circle form, you will see there are four terms: x1 square minus x1, x2 square minus x2. So four features. So that's why I told you intuitively we can see in higher dimension we can separate linearly. So x1 square minus x1 can be one dimension for better visualization, and x2 square minus x2 can be seen as the second dimension to visualize in two dimension. So you can see x1 square minus x1 and x2 square minus x2, and corresponding we are able to draw a line. So this is the idea. So this is the corresponding circle equation that can be seen as the transforming function: x1 square, x2 square, root 2x1, root 2x2, and 1. So, but again, so first important point, why in higher dimension we can say the objects are linearly separate. So this example will provide some foundation regarding that one. Second point one is how to deal with the computational complexity. I want to tell you that's why kernel trick came into the existence. So when we are transforming our data objects into higher dimension for dealing with non-linearity in the objects. So first important point, transformation function is required. So we are not able to find out optimal transformation function. Okay, and the transform function is not given to us. Then if it is given to us, then again another issue, the computational complexity. So rather focusing on the transformation function, we will focus on the kernel methods. So I want to tell you why. Just I am backing soft SVM dual form. So this is a dual form. Here you can see the first term has only alpha I, Second term has alpha i's, and objects are appearing in the inner product. I have emphasized initially also xi transpose xj. Suppose a data set has nature in non-linearity, then we have to transform every data object into higher dimension through some transformation function. So what will happen? Phi xi transpose, suppose phi xj. If phi is given to us, then we can do, but again computational complexity came into the existence. So rather we are, suppose this is the after transformation, these objects will appear in higher dimension in this fashion. So we can take kernel kx1 x2, this is the kernel function which is equivalent to this transformation function phi x transpose or phi xj. So we can take directly the kernel, rather transformation function which is equal to this one. Then this kernel can be used rather. So kernel will help in reducing the computational complexity. There is no need to multiply. We believe you use direct this result. So this is the idea about the kernel methods. So I think I am taking some example so that you can understand. So in the previous discussion, suppose this is a transformation function. I am assuming it is given to us. So phi x transpose and phi x2 I am taking here y1 y2. So after multiplying other term for the y1 y2, what is y phi y1 y2 will be 1 root 2 y1 root 2 y2 or y1 square y2 square and root 2 y1 y2. After multiplying those two terms, you will get this expression. So after, I am saying that we will use direct this expression as a kernel function. We will not multiply that one because we don't have the transformation function. We will use directly the kernel function, hit and trial method. So we will, so research has been started to find out optimal kernel function. It is in the input space, you can see here. So some popular kernel functions are evolved. So first popular function is kernel, polynomial kernel with degree d. These are the data objects x, y, or x1, x2. You can take x1 transpose x2 plus 1 d. This is a radial basis function, e to the power minus x1 minus x2 whole square 2 over sigma square. It is related to Gaussian. That's why it is called radial basis function. Similarly, third one is tan hyperbolic k x transpose y plus theta. So these are the popular kernel functions which can be used directly. Researchers have found out these, evolved these kernel functions. So again, another issues came into the which kernel is more optimal. So there is no hard and fast answer. So you can start with the quadratic kernel, linear kernel, or exponential kernel, or radial basis kernel, or tan hyperbolic. These are the popular ones. So you can take these initial try. Another important point regarding how to design a kernel function, new kernel function. So I want to just introduce research regarding the kernel function. So before discussing the kernel research, I want to tell what are the changes in dual form of kernel based SVM. So these are the soft SVM dual form. So after kernel function, it will be changed. In place of phi xi transpose, phi xj will be changed as kxi xj. And what is the solution of this one? What is the solution of original one? W I equals 1 to Tj, alpha Tj, ytj, or xtj. So you can see, and xtj will be changed. This is the solution of the original one. So again, we are using the transformation function, it will be phi xj. But because I told we will use directly the kernel function when we are classifying the new ones, then wtz. So it will be x tj or plus b. When we are transforming, you will get a phi x tj and phi z. So it will be just like a kernel kx tj xz. So only two change. First change is this one, and second change when we are classifying the new data objects, this one, when we are using kernel based SVM. So kernel based SVM is generally preferred. The reason behind it, we don't have in advance data set is linearly separable or not. That's why kernel based SVM is preferred. If we know the data set is linearly separable, then we can go hard or soft SVM. So this is regarding the kernel. Now I want to introduce how to design a new kernel in the research of kernel-based machine learnings or kernel-based support vector machine. So I want to tell you kernel function just like a similarity measure. So similarity measure has three properties. Reflexivity means symmetry property. So means two objects are similar, x1 x1, that similarity will be +1 or similarity will be non-negative. If x1 similarity between x1 and x2 and x2 and x1, so that is symmetry. And triangle inequality. So we can say similarity function can be seen as an alternate of kernel function. But so you have some idea, you have idea about the similarity functions. So similarity functions like Euclidean distance functions or Pearson correlation, cosine similarity, these are the similarity function that can be an alternate of kernel function as well. But question arises, when how can we say that every similarity function will be a kernel? No. So there is a need of some mathematical concept. Mercer condition should be satisfied. So what is Mercer condition? We can make the kernel matrix, and that kernel matrix should be convex or positive definite. That is the Mercer condition. So so this is the idea how to design new kernel function. We can take similarity function, or we can take any function if that is satisfying the three properties of similarities, then we can say that is similarity function, and that similarity function is satisfying the Mercer condition, then we can use that kernel. But I am not saying that that kernel will provide a good result. If that a particular kernel is providing good results in different data sets, then you can use frequently that kernel. Now I am taking some example of the discussion. Suppose we are taking very small data set for the computation perspective. Here in this data set, 5 one-dimensional data point. So x1, x2, x3, x4, x5. So x1 value is 1, one-dimensional. It is representing by only one feature. x2 and x3 is 4, x4 is 5, and x5 is 6. And it is given to us also 1 2 6 as class 1, means it is class 1. y1 will be 1 or y2 will be 1. Similarly, y5 will be 1, and remaining ones will be in the class 2, means y3 will be -1, y4 will be -1. Now we will use this data set for the kernel based SVM. So first of all, what is the appropriate kernel? So I told earlier there is no hard and fast rule. So we are using polynomial kernel of degree 2, means quadratic kernel. So I am using 2 data points xy that will be represented as a quadratic kernel xy plus 1 d in place of d. I am using here 2. And in the kernel base, because soft SVM I have transformed in the kernel, so C should be trade-off parameter. So I told earlier it should be decided empirically. So here I am, for the mathematical perspective, we are using C as a 100. So what will be the objective function in the kernel based SVM? So just remember here, in kernel based SVM, the objective function, dual objective function will be here. So n will be 5. So alpha 1, alpha 2, alpha 5, 1.2, alpha a, alpha 5, 5, y1, y2, and kernel kxi, xj. So 2 objects. C is 100. So we will use this one in this example. Okay, xi, xj plus 1 square. And C is the trade-off parameter, and this is another constant of dual objective. So we are using here kernel function that is given here, 2 data point x1, xy. Y is not a class label here. X1, x2. So that's why xi, xj. Now, how to decide and what is the solution? So after solving this one, you will get some of the alpha i's are non-zero and other ones are 0. So because these are this very small data set and I am not telling how to solve this one, we are taking the result directly. So after solving, we are getting alpha 1 is 0, alpha 2 is equal to 2.5, alpha 3 is 0, alpha 4 is equal to this one, alpha 5 this one. So out of 5, we are getting 3 non-zero and 2 zeros. No issue because of the small data set. In the large data set, most of the alpha i's will be 0. So corresponding alpha 2 corresponding data object x2, x4 and x5 will be the support vectors. So x2 value is 2, x4 value is 5, x5 value is 6. So how to decide how to decide the class label of new objective, new data, new object? So fz, discriminant function, which I told, changes. This is the deciding new data object fz, alpha I, yi, alpha I we are taking only those ones which are the support vectors, and z is the new data point, and xi. This is the kernel function. So we will use those ones here. Fz, what is the fz? I'm just using that one directly here. Xi belongs to support vectors. So alpha I, only 3 support vectors here. Alpha I means 2.5, alpha 2. Alpha I and y. What is y2? Y2 is -1. And kernel. Kernel means x2z. So x2z means 2z plus 1 whole square. So not -1, plus 1. Initially, y2 will be plus 1. So this one, the first term. Similarly, third and third term. Only 3 terms will be here. Reason, 3 support vectors plus b. So after solving this one, fz 0.667, you just square it and compute it. And b is also unknown. Then how to find out this b? You can use any data set point. You can take first data set point x1. You know the class label. X1 class label is +1. So fz will be +1 and x1 value will be put in the place of z. You will get the value of b. Or you can take x2 value. x2 value is given to us and the class label is also +1. So fz will be +1. Anyone you can use in the training data set point. So B can be found out easily. So you are getting this discriminant function. So now you are able to decide the data points class label. If new data point Z is coming into the picture, the value of Z will be put here. And after solving this expression, if it is non-negative, then you can say Z belong to class label +1. Otherwise, it will be in class label -1. So this is the, in this I have taken simple example. And you can see this is a quadratic. So one variable here and second variable is Z here. So that is just like a parabola. So you can see this is a parabola. This is a graphical structure of discriminant function. So till now I have discussed 3 types of support vector machine. Now I will discuss some not machine learning statistical concept that is very important. Generally, in any machine learning algorithm, we are focusing only one thing: how to enhance the accuracy, or how to find out the parameters. If parameters are very high, then it is very hard to estimate. So I'm saying that Wapnick has told 2 important aspects. Parameter is also important aspect. Second one is flexibility of the classifier. Flexibility of the classifier can be seen as a VC dimension, Wapnick-Cherwonski's dimension. So here you can see one parameter. Suppose this is the discriminant function. Only one parameter alpha here. And it is able, this is a sign function and it is able to classify. That is very flexible. Means only one parameter, that's why it's very flexible, but it is not good. So what is VC dimension? VC dimension can be seen as a number of maximum scattering point. Maximum scattering point means, suppose in 2 dimension. Listen carefully. VC dimension is very important term related to SVM. As the VC dimension means flexibility of the classifier. Referred to VC dimension can be seen as the flexibility of the classifier. So I want to tell you what is the VC dimension. Just it is a theoretical concept. It is hard to estimate, but by taking some examples, you can visualize what is the VC dimension. So VC dimension means maximum number of scattering points. Maximum number of scattering points. This is the definition of VC dimension. Suppose because SVM works on the linear boundary, what is the starting with the hard SVM separating linear boundary in higher dimension we are focusing on the linear boundary. So linearity is very important here in the SVM perspective. So we are focusing on the linear classifier. Through some example, I want to tell you what is the meaning of scattering point. Suppose linear classifier. Suppose only one point here. On training data set has only one point. So suppose, or it is a binary classifier. So suppose it is belonging to class label +1, then we are able to draw a line, no issue. If it is belonging to -1, then no issue. Only one data object in the data set, which will +1 or -1, no issue. We can draw the line. Suppose 2 objects. And suppose it is +1, it is -1, then we are able to draw a line. And you can change -1 or +1, again you are able to draw a line. So when we are only 1 point, no issue. When we are only 2 points, no issue. Now I am extending 3 points. So 3 possibilities. Again, important point. It should not be in the collinear. So 3 objects. Suppose all the possibilities I am taking, these two class label plus 1, this is minus 1. And in all the cases, we are able to draw a line. Collinearity will not be involved. Suppose now I am adding another point, 4 points. Now you can see I am not able to draw a line in 2 dimensions. So what does it mean? For the linear classifier in 2 dimensions, 3 is the critical number. Only 3 data points can be clearly shattered by the linear hyperplane. So 1, 2, and 3 and 4 does not. So maximum number of scattering point is 3. So here the linear classifier in 2 dimension, the VC dimension is of linear classifier in 2 dimension is 3. So that is the number of scattering point, maximum number of scattering point. So the classifier should be flexible. It is if the classifier is more flexible means higher dimension, higher VC dimension. So it should not be allowed. Now I am coming back why support vector machine follows VC dimension. So just these are the same idea which I told you. Coming back to the this term. Where is this one? I want to tell you. Just I am just taking in SVM. So okay. So in SVM, as you remember, objective function, the first term is like W square plus second term is like this one, error term. So second term is generally related to, because we are I am not focusing on the accuracy, we are focusing on the error minimization. Trade-off parameter C will be here. So 2 important points we are discussing together. So support vector machine automatically handles the flexibility of the classifier. That's why it is closely related to statistical learning theory. So this is the same thing as I told in more detail. So question arises, suppose when another important concept related to SVM is structural risk minimization. So suppose classifier 1 means first decision boundary and second decision boundary. Which one will be the better? So you can see in this figure, after training support vector machine, we have got 2 classifiers by setting the parameter C. By taking 2 parameters, suppose C value is 5 and again I am taking C value is 10. So we are getting 2 classifiers. Which one will be the better? Because as I told earlier, C will be decided empirically. So how you will say this C is optimal? So I want to tell you. So increasing error rate. So training error will be here. Okay, and this is the testing error. So the confidence interval will be the difference between the testing error and training error. Here you can see in the second classifier with the different value of C, training error is higher, but the testing error here is minimized. So confidence interval is smaller in comparison to first classifier. So I am just concluding, if the confidence interval is small, that will be the good classifier. So for deciding C trade-off parameter, we will take different values of C. Then we will, after taking different value of C, we will train different classifier using support vector machine. Then we will check the confidence interval. If the particular value of C, the confidence interval is smaller, that C will be the optimal. This is the idea how to decide C. Now, so all these things have been discussed already. So as I told earlier, which kernel will be used? So I told earlier, there is no hard and fast rule. You can start with linear kernel, polynomial kernel, radial basis kernel. Now I want to tell you, because I have started binary classification. So question arises, how to deal with the multi-class problem in support vector machine. So I have discussed everything in binary classification, but it is not always possible. Then how to deal multi-class problem using support vector machine? So suppose 3-class problem. So I want to tell some idea how to deal with. So suppose first class is +1, second class is 2, and third class is 3. So we can combine these two one and this one. So that will be +1 and that will be -1 pairwise. You can combine 2 or 3 as well. So 1, 2, 3. Again, that will be -1, that will be +1. So you can make corresponding pairs. And for every pair, you are using intuitively binary classification. So we will train the support vector machine for every pair. Clear? Then we will choose that pair which provides higher accuracy. So this is the idea about support vector machine, which deals with multi-class problem. One versus all classifier. These are the some softwares available which can be used in support vector machine implementation. Python library is also available, and all these things have been discussed. These are the strength of SVM, and these are the weaknesses. There is no hard and fast rule to use optimal kernel function. Now I want to take some demonstration if time permits. Hello? Hello? We want to demonstrate diabetes problem for
Go for
using
some.
Python library if time permits. Hello? Only 15 minutes or 10 minutes are required. This is the foundation of support vector machine and mathematical foundation, as well as how to deal with different issues. Now I want to use some Python implementation in Google Colab. I think everyone has some idea about Python library. So the code has been written here as well. So this is the running, just allocating some connecting. Here you can see. After connected, we will use okay. So you can see here in Python libraries, NumPy has referred to as NP and pandas as referred to PD. So NumPy will be used as a numerical computation as an array, and pandas will be used as data framing. And another one is sklearn. From sklearn, we will pre-processing task. Pre-processing why is required, I want to tell you. Features have different ranges. So normalization is required. So that why pre-processing will be done. So from sklearn library, we will import standard scalar. Similarly, for learning support vector, in the training of support vector machine, we have to divide our data set into two categories, training and testing split. So we will use model selection by importing this one using sklearn. And for training perspective, SVM directly we will import. And how to find out the accuracy of trained SVM, we will import accuracy score. So these I am not using any graphical representation. That's why we are not using matplotlib. So after running it, we are getting this one. Now we are taking another data set. So in this data set, PIMA data set, so what is the, I want to tell you what is PIMA data set. In the PIMA data set is, it has been given into Kaggle repository. So in this data set, female candidates data has been collected. And in the female candidates data set has been categorized into two categories. A female is diabetic or not, based on various features. So I will discuss those features as well. So that data set is available and we have to read in the data frame. So that's why we are using, that is the variable diabetic data set, and PD is the pandas library, and read as CSV files, and this is the path. Suppose it provides an error, means we have not uploaded. Just I want to run it, you will get in some error. You can see here this error because we have not uploaded this data set. So first of all, we will upload. No data set is available. So we have to upload the data set first from this one. Diabetes. So it has been uploaded. So what will be the path? You can see this path, and path is right here. So I think we will not face any problem. If we are facing problem again after running this one, then we have to copy this path. Okay. Okay, successfully run. So now you can visualize the first 5 rows of this data set. This data set has been loaded in this variable diabetic data set, and we will use this head one. Head provides the first 5 rows of this data set. So you can see these are the features. So after running this one, first 5 rows will be appeared. So this is the first female candidate, second female candidate, third, fourth, and fifth. And these are the features of every female candidate: pregnancies, glucose level, blood pressure, like this. And last one is the outcome, means patient female candidate is diabetic, that will be represented by 1, otherwise it is represented in the 0 in the class label. So binary classification, there is no issue. So this is the, so these are the, I think 1, 2, 3, 4, 5, 6, 7, 8 or 9 features. The last feature is the classification task or decision attribute, that is discrete one, 1, 0, 1, 0. So we will use 8 features are characterizing features, and last one is the decision attribute. So what is the dimension? Means how many female candidate data set is available. So just shape is the function that will provide you how many data sets. So 768 and 9. So data set has 768 female candidates and 9 is rows. Other description can also use just like in statistics, some descriptive statistics can be used, mean, median, mode, like that. So for that perspective, we can use some describe function of this data set, diabetic data set, describe function can be used. So you can see this one. So that is the count 760, mean of pregnancy counts 3.84, glucose level mean is 120. So for every attribute we are getting mean, standard deviation, minimum, quartile 1, quartile 2, quartile 3, and maximum value. Now, because we have to check how many diabetic female candidates or how many non-diabetic female candidates. So we are taking that value counts. So based on the outcome, we will take the value counts. The value counts can be used as the outcome. Outcome will be the last row. So you, after running is, you will get 500 are non-diabetic and 268 are diabetic female candidates. Now we are taking diabetic, because when we are training something, then we have to describe, we have to some analysis about the data set. That's why these things are to be done with, but these things will not be used in the support vector machine. But I want to tell you, suppose a diabetic, what is the analysis of non-diabetic female candidates? What is the pregnancy average? What is the glucose average? So group Y based mean we can compute by running this one. So this is the idea about the descriptive statistics. Now I want to tell you for the training perspective. In this discussion, in Python library, nothing will be discussed as a mathematical. There is no need to, because Python library is always available for the computer science students. This thing is not very helpful, but implementation perspective is quite good. So first of all, I am separating the class labels of the data set. So we are separating the last label, which is the target attributes, which is putting here diabetic data set. And other attributes can be grouped together that are characterizing attributes. So X contains all characterizing attributes having 768 candidates, and Y contains only the class label of those ones. Axis one means column wise we are distributing. So, and this is the variable, and drop means we are dropping that one, distributing those ones based on the outcome. The outcome means last one. And axis one means column wise. Now we will print one. We can print these ones, print X and print Y. So you can see X has only 8 attributes and Y has only 1 attribute. So you can see 768 rows and 8 columns. Clear? And for second one, you will get only 1010, means 1 cross 1. Or sorry, 168 cross 1. So this is Y and this is X, starting from 0. Now I will, as I told, pre-processing is required because every attribute has different range. That's why pre-processing is required, in which normalization can be done. So before training, we have to normalize our data set. So that's why I have imported standard scalar. So we will use that one. Standard scalar is for, it is very big name, that's why we are using a smaller one, scalar. So we are fitting X, means X has been distributed having only 8 characterizing attributes. So fit X and transform. So all the attributes have been transformed in the same range. So that is standardized data. And you can use direct standard scalar transform. So this is the, so you can see the range has been changed. Again, I am just for the simplicity perspective, standard data, I have used a very big name of variable. So I am just assigning as X again. So again, X and Y will be used. So print X and Y, X is same as standard data. So now we have taken standard data X and Y. Y is the class labels and X is the standard data. Now we will split our data set into 2 categories, training and testing. So we will use the second one. So X train, X test, Y train and Y test. So we will call this function train test split, which has been imported already, and we will pass X and Y. Test size means how many, so what is the ratio of training data and test data. So 80 and 20. So 20% data has been taken in the test data set. Stratify, it can be done randomly. Random state 2. Now we will print it, X train and Y train, and we will take the, what is the shape. Shape means how many rows has been taken into training data set, how many rows has been taken into the test data set. So dot shape complete, and what is the training data set and what is the test data set. So after running it, so total data set has having 768 female candidates, 8 characterizing attributes, X-train. And out of that 614 data set has been taken, a female candidate has been taken in the training data set, and remaining ones will be taken in as the test data set. So this one will be used as test data set, and this one will be used for the training perspective, and corresponding y test and y train will be displayed. So now we will use that, we will train that model. So for training perspective, we will call support vector machine classifier. So as I told, for the kernel, we will use linear kernel, which one xy plus 1 plus 1 to the power 1. That kernel I am using, and this is the variable svm.svc. Now we will pass in this classifier variable the data set, training data set. So classifier dot fit x train and y train, corresponding y train will be passed. So after running this, we have trained our model. Now I will check the trained model's accuracy on the training data set as well as test data set. So model evaluation accuracy on the, first of all, I am using the training accuracy. So training accuracy will be based on the training data. So first of all, what will I do? We will predict training data's label. So classifier dot predict will be used, in which X-train data set will be passed. So you will get the X-train predictions, and actual prediction also available Y-train. So based on the X-train prediction and Y-train, you will get the training accuracy. So training data accuracy can be found out by using X-train prediction and Y-train. So if everything is perfectly predicted, then 100% accuracy, training accuracy. Otherwise, some accuracy can be not achieved. So it is very clear, X-train prediction will provide you the class labels of training data set, and that will be compared with the Y-train, corresponding Y-train. Then you will get the accuracy. So you can see here, training data accuracy 78.66%. Similarly, you can find out testing data accuracy, just as X-train by X-test. X-test prediction, just replace, and Y-test. So you will get, so you can see training accuracy and testing accuracy, there is a very less difference. So confidence interval is very less. So that's why support vector machine has directly integration to support VC dimension, or overfitting problem cannot be occurred in support vector machine. Overfitting means confidence interval is higher, means overfitting will be there. If confidence interval is lesser, then you can say overfitting is chance of overfitting will be less. So this is another one I am taking in one instance having 8 values, 4, 1, 2, 3, 4, 5, 6, 7, 8 or 9. Sorry, 8 values. Only 8 values I am passing. I am taking the future data. So I know the class label of this one is plus side -1, I think. So this is the input data because I have trained our model and we have checked the accuracy. Then this model will be used for future data perspective. So that's why I am taking the future data. So what will be the class label? So this is the same attributes in the same range, pregnancies, glucose level range. So first of all, we have to transform it also into pre-processing methods. So because this is the tuple and we have to convert it into the numpy array. So that's why first of all we are converting into numpy array, because we have to compute some mathematical computation. That's why we are converting it. So input data as numpy array. Now we are reshaping. Why we are using reshaping? Because of, and we are standardizing also. So standard scalar transform is also used, because when we have trained our model, we have used the pre-processing. That's why we are using standard data and print that standard data. And now we will predict the class of standard data. So classify dot predict and pass it standard data. You will get the class label. So this is the idea about. So I want to tell you the class label will be 0, means non-diabetic. I have taken this instance from this data set directly. So you will get the class label. This is 0. So we have got same class label. So this is the idea about the Python libraries for implementing any support vector machine for any classification task. So for computer science student, I will refer to write your own code based on some mathematical optimization like tools, and otherwise for other backgrounds you can use direct Python libraries. There is no need of any mathematical formulation and any other thing. So now I want to know if there is any query, please ask. Hello?
Dear participants, now it is open to you. Like if you have any kind of queries, we can ask. It was indeed a very good demonstration as well. It was given to you. So any kind of coding kind of queries also you can ask, and you can clear your doubts now. Thank you.
If you have any doubt, you can you can take my email ID, vibhor.kant@bhu.ac.in. I can write here.
I'm writing, so okay.
And if you have any query till now, then you can ask. vibhor.kant@bhu.ac.in. I have written my email ID in the chat box. And if you have any query till now, you can ask. Otherwise,
So in the meantime, before sir, when the participants are maybe making their questions, let me quickly ask you one thing. So the diabetes, the CSV file, it is available somewhere, or it is your own?
It is available in the Kaggle repository.
Kaggle, okay. Oh,
yes.
it's available in Kaggle. And another thing, the SVM which has been important, that is a built-in library kind of thing. So it does not need any customization or something, or what? Maybe at least for putting some reference kind of vector in SVM, it is not needed, or what?
Sorry, sir.
So this one, like the import SVM which you have.
Okay, this one.
Yeah.
Oh, here I have used this one.
Yeah, yes, sir. In the beginning.
In the beginning, okay. It is available in the sklearn library.
Okay, okay, yeah.
Yeah, this one.
So that does not need any further customization or something?
No, it is directly available. You can use direct, some tutorial is available regarding sklearn library. You can see what are the kernel functions, what are the things. And based on that, you can use directly. There is no need of any customization for the initial perspective.
Okay, okay. Participants, if you have any questions, you can ask, sir. And so there is one more thing, the codes which you have and the project which you have shown is through CodeLab. If it is not part of your research work or something,
okay, I will try to copy it, then I will share it with you as well.
Yes, sir. Yes, sir. So that the participants maybe in the since we have explained in the very deep level coding kind of thing, it will be very interesting for the participants also maybe for trying, and real life examples and data also you have shown, probably they will be very much interested, sir. So if you can please share to me, I'll give to them through the
Okay,
Telegram
sir.
group which has been created.
Okay, sir.
So I guess there is no more question from other participants. So if you have any questions, you can directly contact us, sir, also. The email ID is been given in the chat box. The email ID I'll share to the Telegram group also for your future reference, and you can communicate to him for anything regarding today's lecture.
Okay, sir.
Thank you so much, Vibhor sir, for joining again for our training program. Just like your training program earlier, this was also very much resourceful. It was very interesting because since we have shown a very live examples today, so I was, I mean, keenly following your this one coding style, which is being given now and demonstrations. It is very much useful for me as well for my future research work. Thank you very much, sir, for joining today.
Okay, so it is my pleasure to give a talk in phase 1 as well as in phase 2. In phase 1, I have got some network issues, but in this session, I have got some slightly issue. That's why I have felt very bad again. But it has been started, so I am very happy to deliver this talk efficiently. So thank you very much, sir.
Thank you, sir. So we'll meet again, sir.
Okay, sir.
Okay.
Now
So,
I am leaving, sir.
Yes, sir. Thank you. Okay, sir.
Okay, sir.
So, dear participants, like now it's lunch time up to 2 o'clock. Either you can keep your session active or you can leave for an hour and you can come back exactly 2 o'clock. 2 o'clock, our next resource person will be starting for our session 3. So please join back again. Okay, thank you so much. We'll meet at 2 o'clock. Thank you. So please go for lunch. तो उसमें भी जा सकता है 2 o'clock आ जाओ